Okay, we have a multiple choice question here. We have this wheel axle system, and we want it to be in static equilibrium. So looking at the forces we have acting on it, we're going to have a force here from the gravity on M1 and a force here from the gravity on M2. One's going to create a counterclockwise torque, one's going to create a clockwise torque. So we know that the sum of the torques must be equal to 0. So we can say torque 1 minus torque 2 must be equal to 0. I realize that you might be able to jump to a faster conclusion here, but I'm just going to go through and solve this anyway. So we can say R FG1 sine theta minus R FG2 sine theta equals 0. So we have for FG1, the radius is A, and then it's just going to be M1 times G sine 90 minus B is the radius for torque 2, and it's going to be M2G sine 90. And that's going to be equal to 0. G's cancel out here, and ultimately what we're left with is A M1 equals B M2, which is option B here. For this problem, we have a person standing on a diving board that is massless and has a length of L. We see the person standing there in the middle of the diving board. First question we want to know is what is the direction of the force on the diving board from support B. So I'm first going to think about all of the forces that I have here acting on my diving board. So I have the force of gravity from the person here. Okay, I'm worried about the force from support B. All right, so what I'm going to do is I'm going to set my pivot to be that left end where support A is. And there will be some force from support A. We don't exactly know which way that's going, but it doesn't really matter for this part because we're just trying to find the direction of the force from support B. So what I'm going to think about is the fact that that force from the gravity on the person is going to create a torque going in the clockwise direction. That means that I need a torque going in the counterclockwise direction from support A, or from support B, so we need some torque like that. And that means ultimately that the force from B must be going up, because that's the way I'm going to create a counterclockwise torque. Moving on to the next situation, we're now looking for the direction of the force from support A. So let's think about our forces once again. We have the force of gravity from the object. We know we have some force from support B, and we want to find the force from support A. So what I'm going to do is I'm going to set support B as my pivot, okay? Because I already know that direction, I no longer really care about that. And that means that the force of gravity then is going to create a clockwise torque still, so we need a counterclockwise torque created here to balance. And that means that the force from A must be going down. For part C, we want to derive an expression for the force from support B. So I'm just going to go right back to this setup here. Those are the forces acting on the object. That left side is going to be my pivot. And I'm going to go ahead and do sum of the torques is equal to 0. So the torques that I'm going to have the torque from support B minus the torque from gravity. They're going to add up to 0. I'm going to solve for each one of those by doing torque is RF sine of theta. So for support B, my radius is just going to be L over 4. Okay. The force is going to be the force from support B, of course, and the angle there is going to be 90 because that's the angle between R and where that force acts. Then I'm going to have minus, thinking about the force of gravity, its radius is going to be L over 2 from the pivot to where that force acts. Its force is going to be mg, the force of gravity, because we know the mass of the diver there standing on the diving board. And that also is going to be sine of 90. Once again, that angle between the radius and the force is 90 degrees. So that's all equal to 0. These sines of 90, they just become 1. And what I end up getting is L over 4 times FB is going to be equal to L over 2 times mg. I can cancel out my L's here, all right, and solve for and multiply by 4 there, and I solve for FB, finding that FB is just going to be 2mg, 2 times the force of gravity acting on the person, which makes sense because those torques need to balance, but the force of gravity acts twice as far away, so the force from support B should be twice as much. For D, we want to know as the person walks towards the edge of the board, on the right, will the force from support B increase, decrease, or remain the same? So we can see this from an equation standpoint pretty easily. Keeping that left side as our pivot, if we exert this force further away from the pivot, that's going to increase this number, that's going to increase the torque from the force of gravity, and therefore we need more torque from support B to balance, and the way we're going to do that is by increasing the force from support B. All right. So to balance that increase in torque from gravity, we need a greater force from support B. For this problem here, we have a rod which is fixed about its left end on a horizontal surface, and we're going to take a disc and slide that disc towards the rod. The two are going to collide and eventually rotate together. And what we want to do is we want to have the disc rod system have the greatest possible angular speed after the collision. So the first question says, if we want to give the rod as much angular speed as possible, do we want to make the disc hit over here to the left of point C, exactly at point C, or to the right of point C? The answer here is going to be to the right of point C. And what we're going to think about here is conservation of angular momentum. So initially we have the angular momentum of just the disc. Afterwards we're going to have the angular momentum of the disc rod system. By having that disc hit to the right of C, further away from our pivot point here, that's going to increase the angular momentum of the disc before the collision, which in turn is going to increase the angular momentum and therefore the angular speed of the disc rod system after the collision. There is one line in here that I just want to point out, and that is this part about the rod is much more massive than the disc. What that is saying is that when the disc is added to the rod, okay, that little bit of mass that the disc contributes does not actually impact the rotational inertia or the moment of inertia of the rod. So that's what that line is getting at, that it doesn't really matter where the disc hits on the rod in terms of the moment of inertia of the disc rod system. All that really matters is increasing the initial angular momentum of the disc to increase the final angular momentum of the disc rod system. For part B here, we're given this equation that a student finds on the internet, and we just want to determine whether or not this equation matches our reasoning in part A. The equation may or may not be correct. We just want to know, does it match our dependence in part A that we talked about, where we said that the further the disc hits from the pivot, the greater the angular speed. And we find that yes, this equation does, and we can see that the angular speed here is directly proportional to x, the distance from the pivot. And therefore that does match with our reasoning that as we increase our distance from the pivot, it increases the final angular speed of our system. For part C, we're given another possible equation for the angular speed after the collision, and we're told that it's an incorrect expression, and we want to explain why it doesn't make physical sense. So what is off about this equation? So let's look at how this equation relates angular speed to the various variables. So I see up here that angular speed is directly proportional to the velocity of the disc and to the distance from the pivot, and that makes sense. We've already talked about how increasing the distance from the pivot will increase the final angular speed, and it makes sense if the disc was traveling faster, the angular speed of the system would also be greater. The other two variables, though, don't quite make sense, and the first one is I. Having a greater moment of inertia means it's more difficult for the rod to rotate. So if our moment of inertia was bigger, okay, that would actually mean their angular speed was smaller. However, this equation is showing them as directly proportional, and that doesn't make sense. They should be inversely proportional. The other one that doesn't make sense is the mass of the disc down here. This shows that as the mass of the disc increases, the angular speed would decrease. It's showing an inverse relationship. And that doesn't make sense either, because having a bigger disc here sliding towards the rod means that we're going to have more angular momentum, and that's going to translate into a greater final angular momentum and a greater final angular speed for our disc rod system. Moving on to parts D and E here, so we're told that first of all we're no longer going to make the assumption that the rod is much more massive than the disc. And then we're given some information about this system. We know the disk rotational inertia, or moment of inertia, and we know its angular momentum, and we want to derive an expression for the post-collision angular speed, omega, of the rod. All right? So we're going to think about conservation of angular momentum. All right? And initially we're going to have the angular momentum of the disk. Afterwards, we're going to have the angular momentum of the disk rod system. So for the angular momentum of the disk, we're actually told that it's just the mass of the disk times the initial velocity of the disk times x. That equation, though, is coming from something we've learned, that it's just rp sine of theta, okay? Our radius is that x value there, okay? P is the mass times the velocity, the momentum of the disk initially, and the angle would just be 90, but that's where that equation comes from. Afterwards, we're going to have the moment of inertia of the disk plus the moment of inertia of the rod times the angular speed of the disk rod system, which is what we're looking for. So we have mass of the disk, velocity of the disk times x, and that's going to be equal to the moment of inertia of the disk, which is going to be mass of the disk times x squared, plus the moment of inertia of the rod, which we were told in the very beginning was just I, okay, times our final angular speed. And so when we go ahead and solve for our final angular speed, it's just going to be mass of the disk times velocity times x all over mass of the disk times x squared plus I. It's a slightly messy equation, but that's what we end up getting for this one. Our final question here asks if the disk bounces backwards off of the rod, what effect would that have on our post-collision angular speed? And the answer is that we would have a greater final angular speed than when the rod sticks to it. And I think the easiest way of explaining this is that if the disk bounces off the rod, it undergoes a greater change in angular momentum. And that means that the rod then has a greater change of angular momentum, because when momentum is conserved, angular or regular, the change in momentum for each object is going to be the same. So if the disk experiences a greater change in angular momentum, so does the rod, and therefore it's rotating faster. All right, last problem here. This is an actual old AP problem. So we first want to start with identifying the forces acting on a wheel that is rolling down the ramp. And we see that it is rolling without slipping. That's an important piece. So let's start by thinking about all the forces and where they act. First of all, we have the force of gravity, of course, and that's going to be acting in the center of mass. We also have a normal force, and that's going to act at that point of contact between the wheel and the ramp. Lastly, we need something to get this wheel rotating, and so it's going to be rotating that way, which means we must have a force of friction that's going to provide that torque going up the ramp. Okay, so that's the first part. For part 2 here, what force causes a change in angular velocity as the wheel rolls down the ramp? That's going to be friction, and we've talked about this before in some other cases. All right, and the reason being, friction is the only force that can exert or create a torque about that pivot. Okay, Fg acts on the pivot, Fn would have an angle of 180, so neither one of those can create a torque. All right, so there we have that. Moving on to part B here, and I'm just going to do this up here. So for B, we're looking to derive an expression for the linear acceleration of the wheel's center of mass. Okay, and we do have this one weird line here, that the magnitude of the force of static friction is 40% of the magnitude of the force or force component directed opposite to the force of friction. So that's a little bit confusing. I'm not going to worry about that right now. What I am going to worry about is setting up some of the forces in the x direction specifically. That's going to be equal to max, and some of the torques equals I alpha, because we have both linear and angular acceleration. And thinking about this force of gravity here, okay, thinking about my x forces, I'm going to start with componentizing that. So I know that this is going to be Fg, this is going to be Fg cosine theta, and this is going to be Fg sine of theta. All right. So in the x direction, the forces that I have acting on the object are Fg sine of theta minus Ff. That's going to be equal to max. All right, and here maybe this makes a little bit more sense now. This force of friction, all right, is going to be 40% of this force going in the opposite direction of Fg sine of theta. So what I really end up having is mg sine of theta, just substituting in for Fg, minus 0.4 times mg sine of theta. Okay, 40% of that force is equal to ma. The m's, of course, cancel here, and what we're left with is 0.6 times g sine of theta equals my acceleration. All right, so I actually didn't need to do my torques here, although it's really not a bad idea to always get that set up. I think that's a good habit to get into. Moving on to part C here, we're now considering the case where we have a block of ice released from the top of the ramp compared to this wheel rolling down the ramp. And we want to think about which one will reach the bottom of the ramp. So we know that the ice slides with negligible friction, and the wheel, okay, is still released from rest, rolling down the ramp. So which one reaches the bottom with the greatest speed? That would be the block of ice, okay? And so we want to briefly explain in terms of forces, all right, for the first part. So in terms of forces, the ice has no force of friction, okay? It only has that x component of gravity going down the ramp. And that's going to mean that it accelerates at a greater rate, okay? And so that's why the ice, in terms of forces, that's why the ice is going to reach the bottom first. Part B now asks us to explain the exact same thing in terms of energy, okay? And so the key difference here is the ice has no rotational kinetic energy, all right? And that means that all of its gravitational potential gets converted into linear kinetic energy. So therefore it's traveling faster. And there we have it.